Good morning. Welcome to Things a Little Different this Friday morning, coming to you from the basement of my mother-in-law's house in Akron. I don't mean to keep you long. There's not a lot. We won't be here for an hour. But I did want to talk about a couple more things out of section 2.4. Particularly, I wanted to get you started on the homework, and then you guys can be on your way for spring break. When we get back from spring break, you'll hand in homework 2.3. That would have been handed in today. Just hang on to that. 2.3, we'll get to that. Hand it in after spring break. 2.4, I think we'll probably hand that in the Friday after spring break. That way, for those of you that are going on trips, doing exciting things like that over spring break, give you a little bit of time when you get back to campus to maybe finish this up. But you don't need to see my face the whole time I'm talking, so I'm gonna click on the projector, pull that up to the front of the screen, and then I'll be back to wrap things up. This is what we were talking about on Monday. We were talking about quantifiers. I went over all of this. I remember those of you that were with us, we had the existential quantifiers and the universal quantifiers, and those were indicated by the backwards E for existential and the upside down A for universal. You think of the letter all, or sorry, the word all, the upside down A, and we saw how those are used. And when working with the existential quantifier, we know that the statement is true when at least one of the elements or one of the members of the set is true. And the only time that an existential statement is false is when every single element in the set is false. So if there is absolutely no way that the statement can be true, if there's no value of x for which the statement is true, that's the only time an existential quantifier statement is true. On the other hand, for universal, when we're saying that for all or for every x that a p of x is true, that we're saying it's true for every element of the set, like every integer or every real number, whatever the set is we're working with, and that the universal statement would be false anytime you can find at least one element for which the statement is false. So this is where we talk about the counterexample. To show that a universal statement is false, all you have to do is find one case where it's false. Okay? If an existential statement is false, that means it's false for at least one element in the set. If it's true, if we're trying to show that the statement that for every x it is not true that p of x, then we have to show there exists an x such that it's not true for a particular x. Then we have to go look and find make sure that it's true for every. So if it's true for every element in the set, then this statement is not the case. And to say that for all x it is not the case of p of x, so in other words, for all x this is false, then we're saying that p of a is false for every a because of that universal quantifier. And if we want to show that this statement is false, this statement saying that it is not the case of p of x, then we just need to find one case where P of x is true. Finally, on Monday, just to review, we looked at how you would negate statements. To negate a universal quantifier means that there exists an x such that P of x is false. To negate an existential quantifier means that for all x, P of x is false. And you can see here the idea of the double negative. So you have when you have the double negative with the universal existential, and then when you have the double negative with the existential, you get the universal. So that's what we went over on Monday. Just a quick review. I wanted to just get that up on the video so that everybody could check to make sure their notes are complete. Before we get any further, I just wanted to drop this up here so you guys can see that we've got some homework coming for section 2-4, and it's 4, 5, 7, just ABC on number 7, and then 16, 18, and 19. What I want to do, because I know some of you lugging your book around is not going to be a joy, so I wanted to just go ahead and put these up on the screen. Just put the book underneath this Ziggy. So 4, 5, 7, ABC, 16, 18, 19. Probably want to write that down somewhere. Here's number 4. Okay. And I guess it might be a good idea to zoom in a little bit on this one, just because you want to be able to see what in the world this little tiny print is showing. So let me do that, and we'll call that good. Slide that down into place. Wonder if we can get a better focus on that. Good enough, I guess. So here it says consider the universe of all polygons. So with polygons we're talking about triangles and squares and quadrilaterals and all that stuff. So with that we have these different statements. We have all these different statements about polygons. You have those are the basic statements that we're going to work with, and then down here in part A, B, C, D, F, G, H, I, J, all we need to do is translate either each of these statements into English. So you're just going to write out what each one of these statements is saying in English. So let's take this first one. This is a universal quantifier, and it says for all x, q of x, XOR or exclusive OR T of x. It's not too difficult to put this into plain English. If we said for all x, or for every x, and then q of x, if you look up it says q of x, that means x is a quadrilateral, or, and then T of x says x is a triangle, but because this is an exclusive OR, you want to end with but not both. So x is a polynomial, so we could really do a good job by saying for every polynomial, the polynomial is either a quadrilateral or a triangle, but not both. Okay? For every polynomial, the polynomial is either an isosceles, sorry, I need to back up, start all over again. Part B, for every polynomial, if the polynomial is an isosceles triangle, then the polynomial is an equilateral triangle. Okay? Now, notice what it says up here in the directions, and determine whether the statement is true or false. You may have noticed something there. This says, for every polynomial, if the polynomial is an isosceles triangle, then the polynomial is an equilateral triangle. That is not the case. All right? There exists a polynomial such that the polynomial is a triangle and the polynomial has an interior angle that exceeds 180 degrees. Okay, that's what it says. So the first step is just to translate each of the following statements into an English sentence. But really, if you have a triangle and interior angle exceeds 180 degrees, that ain't going to happen. Okay, so that would be false. So this is how you're going to do number 4. And let me do part D, and then I'll let you loose on the rest to do your own. For every polynomial, all interior angles of the polynomial are equal, and the polynomial is a triangle if and only if the polynomial is an equilateral triangle. So there's your biconditional, which we say if and only if. So we didn't say if then, we just save it for right here. So for every polynomial, all interior angles are equal and it is a triangle if and only if the polynomial is an equilateral triangle. Okay, so hopefully you see that's how number 4 works. Also, you have number 5, and number 5 comes in 2 parts. First is at the bottom of this this column. It gives you some information, and then it continues at the top of the next column. Oh goodness, get that in view. There you go. It has all of these statements, and then what you're going to do is you're going to take each sentence, and you're really basically just going in the reverse of what we did with number 4. So here in number 5, you're going to be taking the quantifiers and the statements up here. You're going to be using those to write a symbolic expression for each one of these statements. There is a mathematics major in the class who is a junior. Okay? So there exists a mathematics major who is a junior. There is a student who is both a mathematics major and a junior. You'll see up here that we have the statement of a mathematics major. We also have the statement of a junior. So there exists an M of X and a J of X. Okay, that's how you're going to do that. So if you just let me scribble this in here real quick. There exists an X such that that person is an M of X and a J of X. Okay? That's what that's saying. There is a senior in the class who is not a mathematics major. So there exists an S of X and not M of X. Okay? So this is going to be the universal quantifier for C. Every student in the class is majoring in mathematics or physics. So for every X in the class, it's either m of x or p of x. Okay? I'll let you finish that up. Number 7. Number 7, again, they set up the problem. You have the universe of all integers. Then you have these different statements for the integers. Part A of this problem, yeah, there it is. For part A, you're going to write each one of these in symbolic form. At least one integer is even. So if you look at the bottom of the previous column, I won't move the textbook around and give you motion sickness. So at least one, so existential quantifier x, and then the integer is even. If you look down here, that's q of x. So in my book, the principal won't get mad at me if I do this. There exists an x, q of x. Okay? Because q of x is the statement that x is even. And there exists a positive integer that is even. Okay, well, p of x talks about positive integers. Q of x talks about x is even. So there exists something that is both positive and even. So it's that this part 2 is going to be there exists an x such that p of x and q of x, both of those. This is going to be a conditional if then, okay, and you can see the rest there. And I just want you to do A, B, and C. Don't worry about D on that. Okay. All right, let me go over to number 16 in the text. Number 16 gets to what I was talking about of writing the negation of these quantified statements. Okay, this is what I had from the notes, writing the negation. If you want to just hit pause, you can see number 16 and you can see what I had written in the notes. They're all together now, they're on the screen. But write the negation of each of the following statements as an English sentence without symbolic notation. And the universe consists of all students at the university where Professor Lenhart teaches. Okay, every student, so that is a universal quantifier. Every student is majoring in computer science or mathematics. Okay, this is the negation of a universal. So when you negate a universal, you get an existential, and then you're going to have the negation of an or statement, which you know when you distribute that, negating the or statement, you get not computer science and not mathematics. So this one, when you negate it, it's going to be, instead of every, it's going to say there exists a student in Professor Lenhart's class such that the student is not majoring in computer science and not majoring in mathematics. Okay? So using De Morgan's law, when you negate an or statement, you negate each part with an and between. And then part 2 of number 16 is quite similar to that. It's just going the other way around. It starts out with an existential quantifier. So you can do that. Number 18. Number 18 is a little more straightforward. 18, you are negating. This is exactly 16a. It's just here it's given to you in symbolic form. Okay? So when you negate the existential, you're going to get universal, and this is not the case. So De Morgan's distributing the negation across this this one's going to be for every or for all x, it is not P and not Q. And then you can see that each one of these is stuff that we've had before. Negating this, you're going to, in negating the conditional, right? You know, you need, if you're going to negate the conditional, you're going to need to change that to not P or Q. And this, in part D, you're going to need to switch this to not P of x or Q of x or R of x. Okay, changing that to the or statement so that you can negate it. And then finally, the last problem that you have for your homework is number 19. And this is where we're talking about the converse, inverse, and contrapositive. Okay, so it's given, you're given a conditional. Okay, and you know the converse is the inverse. So if the conditional is if m is greater than n, then m squared is greater than n squared, the converse would be the reverse of that. So if m squared is greater than n squared, then m is greater than n. The inverse is just the negation. So if it is not the case that m is greater than n, then it is not the case that m squared is greater than n squared. And then the contrapositive is both reversing and negating. So you would say if it is not the case that m squared is greater than n squared, then it is not the case that m is greater than n. Okay? So that's what you're doing in 19, taking each one of those statements and writing the converse, inverse, and contrapositive. Okay? I hope that this gives you a little bit of a head start on each one of these problems so that you can bust this out. And if you have any questions, be sure to write those down, make note of it. When we get back after spring break, we will regroup, make sure that we give everybody a chance to get cleared up on anything that you don't understand. And it's been kind of a crazy week, hasn't it, with the weather and everything else, but I think we'll be able to recover just fine if you'll get this homework done. And then after we get back from spring break, we'll have a couple days to regroup and get going again. All right, thanks everybody for your understanding. We are having a good time as family being together. It's of course you can understand it's sad for the reason that we're together, but Leslie's father is at peace and is resting well, and we will have, looks like in the next few days we'll have the opportunity for a lot of folks to come together and celebrate his life. You guys have a great spring break and enjoy your family. Give your loved ones a hug and just enjoy the chance to have some downtime, and hopefully we'll have some sun, or you'll have some sun where you are. I'm in northern Ohio, though the chances of some sun and good weather. Yeah, right. Okay, you guys have a great spring break, and we'll see you in a couple weeks.